Hey everyone, it's me, Dr. Major. I hope that you are well as you're watching this video. So in this video, I'm going to do a brief introduction to our non-parametric tests or our non-parametric statistical methods. Up to this point, we've been talking mainly about our parametric methods or descriptive statistics. In the chapter that I asked you all to read via the TAs on Monday, you all should have gotten an introduction to how we're transitioning from the parametric tests into the non-parametric methods or non-parametric tests. So just to kind of review, with all of the parametric statistics that we've covered in this class, our independent variable was measured on a nominal scale and our dependent variable was measured on an interval or ratio scale. The four tests that we are going to discuss in this video are important because we're going to be talking about their non-parametric alternatives. So let's start with the first test, our independent samples t-test. We said that we compute the independent samples t-test, aka the pooled variances t-test, when we have a between subjects design and at least two groups. We said that we do the one-way between subjects analysis of variance when we have two or more groups, and again, we have this between subjects or independent measures or independent samples design. We said that we do the matched pairs t-test or the correlated samples t-test or the related samples t-test, three different names for the same statistical procedures when we have two groups and we have one of our within subjects design, so either repeated measures or matched pairs. We said we do the one-way repeated measures analysis of variance when we have two or more groups and we have a within subjects design, or which is our repeated measures design or our matched samples design. So in this slide, we're going to talk about the non-parametric methods. So give you all a definition of those non-parametric methods and then when we tend to use them. So the definition of a non-parametric test are hypothesis tests that are used to test hypotheses that don't make inferences about parameters in a population and to test hypotheses about data that can have any type of distribution. So sometimes you'll hear non-parametric methods referred to as distribution-free tests because we don't lock ourselves into that requirement or this assumption that in the population the data is normally distributed. So we take away that distribution assumption or distribution requirement for doing some of our non-parametric alternatives. We also, in some of the methods that we'll use, they're not necessarily based on a population parameter. Some of them are, but not all of them are based on a population parameter. And if they are based on a population parameter, it's not going to be the mean, it's going to be the median instead. So when do we use these non-parametric methods? So one is when the assumptions are violated for a parametric test. The second is when the independent variable is measured on a nominal scale, but the dependent variable is either measured on an ordinal scale or a nominal scale. Another scenario would be if the dependent variable is measured on an interval or ratio scale, but the distribution of that data is skewed. Or when we have a small sample, some researchers opt to use the non-parametric test when they have a sample that's less than 30. In this class, we'll primarily be concerned with these three reasons for using our non-parametric methods or non-parametric tests. So if we go back to the table that I just showed you a few slides ago, we will talk about, or I'll identify the four non-parametric tests that we're going to discuss in this unit in this class. So whenever you can do the independent samples t-test, but your assumptions have been violated, or for one of those reasons that I just discussed, you're going to use the Mann-Whitney U-test or the Wilcoxon-Rank sum test. Those are two different names for equivalent tests. When you have an independent variable that's measured on a nominal scale, but the dependent variable is ordinal, or if it was interval or ratio, it was skewed, your violations for the one-way between subjects ANOVA have been violated. The assumption, for the one-way between subjects ANOVA have been violated, then you're going to go with the Kruskal-Wallis test. If you could do the matched pairs t-test or the correlated samples t-test, but your assumptions have been violated, or the IV is nominal, the DV is ordinal, or the DV is interval and ratio, but it's skewed, you're going to go with the Wilcoxon-Rank sum test. Finally, if you can do the one or repeated measures in ANOVA, but your assumptions were violated, or you meet one of these conditions up here, you're going to go with the Friedman's test. So these are the 4 tests that we're going to discuss. We're going to start off with our Mann-Whitney, Ure, Wilcoxon rank sum. In most of the tests that we're going to learn, it involves some sort of ranking. Now, ranking is not a complicated process, but I just want to quickly review it so that we are all on the same page as we move forward. So how do you rank? First, you array the data from smallest to largest, and then you assign a rank of 1 to the smallest value, and then increase the rank for the remaining values. So let's practice. If I gave you the following data, 88, 67, 22, 14, 42, and I asked you to rank this data, you would start by arraying the data. So you have 14, 22, 42, 67, 88. 14 would receive a rank of 1, 22 a rank of 2, 42 a rank of 3, 67 a rank of 4, 88 a rank of 5. Straightforward. Now, sometimes we have situations where we end up with a tied rank. So it's not uncommon for us to have a data set where we have 2 numbers that are the same. So how do we handle this? Well, we still arrange the data from smallest to largest, and we put the 2 tied numbers, or the numbers that are the same, next to each other. So here's the data up here. I took the data and I arranged it from smallest to largest down here. And so here we have 42 and 42. So 14 will still receive a rank of 1. 22 will still receive a rank of 2. But notice that for rank 3, we have 2 42s. So technically this would be rank 3 and this would be rank 4. But since they're the same number, it's not fair to make one of the 42s a rank of 4 and the other 42 a rank of 3. So instead, we take the average of those 2 ranks. So this would have been 3, this would have been 4, but we take the average and find out that it's 3.5. So both 42s would get a rank of 3.5. 67 would get a rank of 5, 88 would get a rank of 6. In all of the parametric methods that we're going to go over that require some ranking, you're going to have to rank across groups. But first, you start off by taking all the data and looking at it as just one big group of numbers. So you look at it as one big group of numbers and you put them in order from smallest to largest. So notice that 14 comes from group B, but it's going to be first on our list. 22 is from B, it goes here. 42 is from A, it goes here. So I'm just going to list all of the data from smallest to largest like we've been doing and then assign ranks. So 14 gets a rank of 1, 22 gets a rank of 2, 42 gets a rank of 3, etc., etc. One of the other things that you'll probably have to do with these tests is to also assign the ranking and the data back to its original group. So like I said, 14 comes from group B and receives a rank of 1. 22 receives a rank of 2, comes from group B also. 42 receives a rank of 3 and comes from group A. Notice that, 42, group A, back over here. 67 receives a rank of 4, that's also from group A. 76, rank of B, group B. A rank of 5 goes to group B. 77, rank of 6, goes to group B. And you just repeat this for all of your data. For homework, I want you to practice what we just did. So array the data across the groups, assign the ranking, and then assign the data to its original group. And that's it.